the National Aeronautics and Space Administration's Dryden Flight Research Center, Edwards Air Force Base, California. NASA's program for research into supersonic flight began at Muroc, California in the spring of 1947 with the X-1 rocket airplane. Hypersonic flight research began with the X-15. A great deal of information was obtained in the high-speed, high-altitude, and short-duration flight envelope with the X-series research vehicles. Sustained supersonic flight research continued with the XB-70. Having exploited the potential of these vehicles, NASA required a more advanced flight platform. To fulfill this requirement, a joint United States Air Force-NASA program was initiated using the YF-12. This program would extend NASA's capability into sustained high-altitude, high-speed flight. NASA's use of the YF-12 sought to achieve many objectives. Some of the priority programs include investigation of predictive techniques in new design for structural, stability and control, and propulsion systems. When NASA received the YF-12, significant testing had been completed, providing a ready research platform. The YF-12 is a member of the triple-sonic Blackbird family, a product of the Lockheed California Company facility known as the Kelly-Johnson Skunk Works. The YF-12 was conceived as a high-altitude, high-speed interceptor. Its basic mission, maximum range intercept with an operational radius of over 1,000 nautical miles. The basic design concept was a low aspect ratio double delta wing with the propulsion system located in the flow field where base drag would be minimized. Extensive use was made of existing NASA wind tunnel facilities. Beside the usual lift, drag, and stability testing at low and high speed, transonic measurements were particularly critical. The thermodynamic and aerodynamic loads on a Mach 3 airplane are staggering. The operational temperature range for the YF-12 airframe would be from a minus 65 degrees Fahrenheit to a plus 800 degrees. During cruise Mach, the leading edges and inlets run over 790 degrees Fahrenheit, wing and fuselage 450 to 500 degrees, afterburner and ejector between 900 and 1100 degrees, and the tailpipes are glowing white hot. This airplane, capable of sustaining speeds of over 2,000 miles per hour, overcame a giant hurdle in the engineering and manufacturing state-of-the-art. Lockheed had been working with titanium on a research basis since 1949. An advanced alloy of this metal was selected to achieve the strength-weight ratios required in this hostile environment. Full-scale mock-ups and test rigs were used extensively. A four-body section was constructed and subjected to the heat and stresses to be encountered. From these tests, much was learned about hydrogen embrittlement, heat treat procedures, and forming methods. Test panels of the wing box were built and subjected to loads which would be encountered during typical flight maneuvers. Also, it was necessary to provide a means for the skin to expand with an increase in temperature and Mach number. This was accomplished by using cord-wise corrugation and special methods to attach the wing surface to the spars. A hot forging process is used to bend and shape titanium billets into structural segments of the airframe. Extremely high pressure and controlled environment are required to form the complex shapes. The practical machining of titanium required the development of cutting machinery, drills, power heads, profilers, and lubricants. The manufacturing of close-tolerance titanium sheet metal parts required a completely new process referred to as hot sizing. The hot press applies pressure to the parts, holding them at a constant temperature and pressure for the processing period. A comprehensive series of static and proof tests were conducted to substantiate structural integrity. 93% of the structural weight of the YF-12 is titanium. Functional mock-ups were used to prove systems before installation. The complete fuel system was subjected to elevated temperatures in climb, dive, and all aircraft flight conditions. Components of the pumping, refueling, purging, feed, vent, and dumping systems were operated at temperatures above 500 degrees Fahrenheit and at altitudes above 80,000 feet. Landing gear components were tested to destruction. Standard aircraft tires would not stand up to the elevated temperatures. A radical design was required to endure the long heat soak of Mach 3 Plus flight. Landing gear tests were run on the drop tower. There were no hydraulic fluids, pumps, or seals that would operate continuously at 600 degrees Fahrenheit. The automatic flight control system, servos, actuators, and cables were installed in an oven and tested for hundreds of hours. Conventional control cables did not pass the test. A watch spring material known as L-Gilloy was used to meet the life cycle requirements. The automatic flight control system includes, in addition to the mechanical and hydraulic components, a stability augmentation system, autopilot system, and Mach trim system. This provides stable flight throughout the wide range of operation. Safety of the flight crew was the prime consideration in the design of the escape system. It was essential to provide safe egress throughout the complete flight spectrum from takeoff to cruise. High-temperature electrical and electronic components were practically non-existent. Wires, terminals, connectors, and transducers developed for the space age were capable for short-duration temperature bursts, but not sustained high-temperature flight. The cockpit, missile bays, and components required a cooling and pressurization system far beyond the capability of existing design. This brought about an innovation, utilizing inlet bleed air and using the aircraft fuel as a heat sink. Inlet bleed air is in the range of 800 to 900 degrees Fahrenheit. Cooling with this air required a unique approach in the design of air turbines and heat exchangers. The air inlet system involves positioning the spike and matching various bypass airflows. The purpose is to maintain the optimum shock position on the cowl to maximize thrust and minimize drag. In the event of an aerodynamic disturbance in the inlet, known as an unstart, rapid sensing of the various parameters is necessary to regain control of the airflow. The disparity in thrust during an unstart is compensated for by the stability augmentation system. This provides aircraft control compensation in a fraction of a second. It is extremely difficult for the pilot to manually correct for such disturbances. The YF-12 fuselage is equipped with compartments in the chine area to accommodate the missiles. Missile loading and static drop tests were conducted. The fire control radar was tested for target search and acquisition above and below and at long distances, beyond the launch platform. live missiles were launched against a variety of drone aircraft targets. Target interception and destruction was demonstrated. On May 1st, 1965, the YF-12 demonstrated its excellence by capturing 9 speed and altitude records in one day. Kelly Johnson, Lockheed's senior vice president and chief engineer on the YF-12, has often said, everything on the Blackbird, from rivets and fluids up through materials and power plants, had to be invented from scratch. The NASA Flight Research Center received the YF-12 in 1969. The initial program objective was to compile instrumented flight data against which various predictive design tools could be compared in order to assess the state-of-the-art of those predictive design techniques. These tests would contrast early transonic B-47 high aspect ratio wing research data with the low aspect ratio wing data of the YF-12. It also offered an opportunity to compare loads and structures data from the rapidly accelerating X-15 research airplane with the long heat-soaked cruise of the YF. NASA and U.S. Air Force Flight Test Center personnel prepared the Blackbird for its new role. Thermocouples and strain gauge bridges, along with other airplane instrumentation, was installed. Point loads were applied to the airplane under ambient temperature conditions to calibrate the gauges. A flight test matrix was selected, flying varying configurations of weight and center of gravity at cruise speeds up to 3 times the speed of sound and at altitudes up to 80,000 feet. Temperatures were recorded for each configuration throughout the entire flight. In addition to loads and temperatures, structural deformations were measured at all test points. In order to precisely calibrate the thermal effects on the strain gauges, ground heating tests were conducted. A stainless steel oven conforming to the contours of the airplane was built. Heat lamps were wired inside the oven. The entire airplane was placed in the test fixture and heated to flight-measured temperatures to calibrate thermal effects on the strain gauges. The tests were controlled by a digital computer program using in-flight temperature time histories. Ground vibration tests were conducted to aid in defining the structural mode shapes. The calibration of the experimental instrumentation and the flight tests formed the nucleus of the empirical work, thus paving the way to assess the state-of-the-art of the predictive techniques. The theoretical work was built around 2 large computer programs known as Nastran and FlexStab. Nastran is a finite element program that predicts structural behavior. This program was developed as part of the NASA space program, and the YF-12 exercised its application to aircraft to the fullest. Utilizing nearly 8,000 degrees of freedom, it took several hours to compute the behavior at each desired condition. FlexStab modeled the YF-12 with some 350 equivalent panels and was used to predict the external aerodynamic loading on the airplane. FlexStab predictions were augmented with pressure distributions measured on a 1/12th scale model of the airplane. This structures research has been completed and reported to the industry at a classified symposium in June of 1974. This work provides an accurate design model for future aerospace vehicles. A current program directed by the NASA Langley Research Center will concentrate on the development of new lightweight structural materials and fabrication techniques. 2 new types of titanium panels have been fabricated, tested, and are acquiring service life history. One uses a weld-brazed process, and the other is of titanium honeycomb construction. A series of composite panels is under consideration. A boron aluminum honeycomb panel will soon be tested. One major objective of the panel program is the determination of realistic cost information for the fabrication techniques. One of the most important facets of NASA research is the Performance Propulsion Program. The theory in these disciplines is not as highly developed as in the structures area. Therefore, greater reliance is placed on wind tunnel testing. The inlet on the YF-12 is a vital element in providing efficient high Mach cruise performance. Air is compressed to 40 times ambient pressure as it slows from free stream velocities in excess of Mach 3.0 to Mach 0.3 at the engine face. A translating center body controls the shock waves for efficient deceleration of the inlet air. Bypass doors precisely match the inlet air to the engine face. Dynamic variations in airflow occur rapidly. Therefore, improper matching of airflow, even momentarily, builds pressure in the inlet and suddenly expels the shock waves, increasing drag drastically. This situation is referred to as an unstart. During an unstart, the airplane gyrates violently due to the aerodynamic disturbance surrounding the inlet. Full-scale inlet tests were performed in the NASA Lewis Research Center 10 by 10 tunnel. A 1/3 scale inlet model was fabricated and installed in the NASA Ames Research Center unitary wind tunnels. The model duplicated the full-scale inlet, but the tests stressed dynamic measurements. It was tested to speeds in excess of Mach 3. 3 YF-12 Pratt & Whitney J58 engines were operated in the high-altitude Lewis Research Center Propulsion Simulation Laboratory. Tests were run to calibrate engine airflow under varying simulated flight conditions. Engine products of combustion were also surveyed. The analysis of dynamic data is a relatively new art. The dynamic data analysis computing setup prepared by North American Rockwell for the B-1 airplane is being used to process the YF-12 dynamic inlet data. Ground-based as well as airborne photographs of the YF-12 exhaust wake have disclosed that long-term wake dissipation characteristics are not predictable with present theory. In addition, U-2 aircraft from the NASA Ames Research Center have probed the YF-12 near-term exhaust wake to make comparisons with the products of combustion as measured by Lewis Research Center. Follow-on work is being considered for the YF-12 inlet research program. Fast-acting pneumatic poppet valves are being placed around the periphery of the full-scale inlet at the Lewis Research Center. Small-scale wind tunnel tests indicate that such a mechanization can reduce the occurrence of unstarts and permit more efficient inlet operation. It remains to be seen if the small-scale results can be duplicated in flight. Other wind tunnel tests have helped to establish the feasibility of testing a modern inlet by placing it on the back of the YF-12 between the vertical tails. This installation can be put into place and removed quickly and easily and permit the evaluation of a wide range of inlet geometries in a cost-effective fashion. Experience on the B-70, the YF-12, and more recently on the Concorde shows that as speed and altitude increase, the ability to hold altitude precisely becomes more difficult. Several factors influence this deterioration in ability to control altitude. At high Mach number, the large energy vector dictates that if airplane attitude changes, even slightly, vertical velocity will change, and so must altitude. But perhaps more importantly, the outside air temperature at high altitude can change abruptly because so much distance is covered in such a short time. These excursions far exceed any values that could be tolerated in air traffic control. The examination of data from many flights showed that the inlet bypass air was the most significant factor in the thrust change produced by the temperature variations. Tests were run on a 1/12th scale model of the airplane at the NASA Ames Research Center to examine the problem in a more systematic manner. Using the 1/12th scale data as well as flight data, an extensive simulation of the airplane and its propulsion system was mechanized at the Lockheed Bry Canyon facility. An autopilot mechanization of altitude hold was synthesized to reduce altitude excursions by an order of magnitude in flight. Further mechanization hopes to make more optimum blending of airframe and propulsion system controls. The YF-12 is carrying a series of aerodynamic experiments into the high-speed regime as a sort of flying wind tunnel. One, called the aft-facing step, measures the base drag behind an inclined ramp. Data from this experiment will give insight into the effects of manufacturing tolerances of lap joints, probes, or other protuberances under boundary layer and Reynolds number conditions unobtainable in existing wind tunnels. Skin friction and boundary layer growth have been measured on the long, straight underside of the YF-12. Since skin friction drag can account for as much as 1/3 of total drag at Mach 3, it is important to be able to predict it accurately. This is an extension of work begun on the B-70. As with the aft-facing step, the boundary layer measurements made in flight cannot be reproduced in any existing wind tunnels. Pressure surveys are also being made on the rear fuselage to get a better understanding of fuselage boat-tail drag effects in a real flight environment. This is another area where difficulties have been experienced with accurate wind tunnel drag measurements, especially at transonic speeds. A series of cruciform delta wings have been added to the nose boom. Differential pressure measured from opposite wings allow for the resolution of gust velocity measurements as small as 1 foot per second. This is remarkable when the total velocity approaches 3,000 feet per second. Gusts and turbulence have been experienced at even the highest altitudes flown on the YF-12. These atmospheric phenomena exert measurable, unfavorable effects on the dynamic inlet behavior and on the flight crews. Flight crews are wired for sound on every flight. Measurement of heart parameters as well as exhaled gases give a continuous evaluation of the effect of high-speed flight on the human. Long periods of flights in the pressure suit cause dehydration and fatigue. It has a treacherous, gradual, and cumulative effect on pilot performance. Efforts are also being made to correlate the relationship between biological measurements and crew workload in order to quantify crew workload. The most spectacular aerodynamic experiment, at least in looks, is the hollow cylinder cold wall experiment. The idealized aerodynamic shape of a cylinder, 10 feet long and 18 inches in diameter, is cantilevered 4 feet below the underside of the fuselage. The cylinder is immersed in nitrogen to cool it to minus 100 degrees Fahrenheit. It is covered with an insulating blanket, flown to Mach 3, and the blanket is pyrotechnically removed, exposing it to a temperature of 500 degrees. Instrumentation built into the cylinder will make a variety of measurements such as heat transfer coefficient, boundary layer transition, and aerodynamic noise, all free of the constraint to wind tunnel wall interference effects. By testing the same cylinder in the wind tunnel, the tunnel interference effects can be better understood and calibrated. This is the YF-12, a national asset, a vehicle providing advanced research today for tomorrow's industry, a flying wind tunnel, furnishing NASA with the technical data to keep America the world leader in aerospace.